Hi students, have a nice day. In this section we are going to discuss about the first law of thermodynamics and its applications. In the last section we discussed many processes and the zeroth law of thermodynamics, internal energy. What is internal energy? You know that internal energy is the total energy of the system. It is a sum of all type of energies in that system. Okay, so based on the internal energy, Helmholtz proposed the first law of thermodynamics. Who proposed the first law of thermodynamics? Helmholtz. 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 Okay. So Helmholtz states that the energy of an isolated system is constant. First law of thermodynamics states that the energy of an isolated system is constant. The law is also known as law of conservation of energy. Law of conservation of energy. That is, energy can neither be created nor be destroyed. Energy can neither be created nor be destroyed. Okay, so that's about the law of first law of thermodynamics. So let's represent the first law by mathematical method. Suppose a system having U1 internal energy. Okay, a system has internal energy U1. What is internal energy? The total energy, the sum of all energies in the system. The initial energy is U1 and the system absorbs Q amount of heat. Okay, it is internal energy and the system absorbs Q heat. Q amount of heat is absorbed. Also, W work done is on the system. W work done. W is work done. W work done on the system. Okay, W work done on the system. The final internal energy of the system is U2 is equal to U1 plus Q plus W. According to law of thermodynamics, first law of thermodynamics, energy can neither be created nor be destroyed. Okay, the final internal energy of the system is equal to U1 plus Q plus W. Okay, U1 is the initial internal energy. Q amount of heat is supplied to the system or given to the system. Also W work done on the system. Okay. So according to law of thermodynamics. Okay, first law of thermodynamics, U2 is equal to U1 plus Q plus W. Okay, rearranging the equation, U2 minus U1 is equal to Q plus W. And we know that U2 minus U1 or U final minus U initial is internal energy change. So delta U is equal to Q plus W. This is the mathematical representation of first law of thermodynamics. Okay, mathematical representation of first law of thermodynamics. Delta U is equal to Q plus W. Okay, delta U is change in internal energy, Q is heat, okay, heat absorbed by the system, and W is the work done on the system. Okay, then as you know that work is a path function. Okay, work done is a path function. And the mechanical work W is equal to P delta V. Okay, So W is equal to if the work is done by the system or work done on the system, W is equal to P delta V. If work done on the system, W is equal to plus P delta V. Remember that it is work done on the system. Work is on the system. And if the work done by the system, W is equal to minus P delta V. Okay, P delta V. It is by the system. By the system. This already discussed in the last section. Work done on the system, work done by the system. Okay, are you clear? Okay, then we discuss about the compression work and expansion work. Compression work and expansion work. What do you mean by compression work? Compression work means the work done on the system. Okay, work done on the system. Expansion work means work done by the system. Consider 1 mole of ideal gas in a cylinder which is fitted with a frictionless piston. A cylinder which is connected with a frictionless piston. This is a piston. Okay, a frictionless piston. If the volume, suppose the initial volume is V1 or V initial, VI, okay, VI, and a cylinder which contains 1 mole of an ideal gas, 1 mole ideal gas. Suppose the external pressure is more than that of the internal pressure. Okay, the pressure of the gas is P. Let's take P internal. And the outside pressure is P external. That is written as PEX. P external. This is P internal. Suppose the external pressure is more than that of the internal pressure. What happens? The piston moves inward. Okay, the piston moves inward. Now the piston is at this area. And the volume changes. Initially the volume at here. Now the volume is V2 or V final. Okay, V final. And also we know that W is equal to force into displacement. Force into displacement. Force is equal to pressure into area. Okay, pressure is force exerted per unit area. So force is equal to pressure into area. So force we have to write that P into A. And the movement of this piston, the distance moved by a small distance dl. Okay, a small distance moved by the piston. So we have to write in the displacement is dl. Then P is equal to, due to the external pressure, we have to also write that P external, A into dl, area into length. We know that it is dV. And the volume decreases. It is minus dV, P external dV. The volume is decreases. So V final minus V initial is negative. Okay. So W is equal to P external dV. On integrating this equation, W we have to write that minus integral Vi to V final P external dV. Okay, P external dV. This is one of the equation. And another equation W is equal to P external. Okay, minus P external V final minus V initial. V final minus V initial. V final minus V initial is negative because final volume is less than that of the initial volume. So the work done become positive. Okay. So also we have to write that minus P external delta V. So we have two equations. This is one of the equation. W is equal to minus integral Vi to V final P external dV. Okay. And by applying the lower and higher limits, upper limits and lower limit, we get P external Vf minus Vi, that is P external delta V. And remember that the work done is positive. Okay, V final minus V initially is negative, and negative is multiplied by negative, we get the work done is positive. Okay, so you understand that two equations. One equation is W is equal to P external dV. Okay, and integrating this equation we get the work done, total work done. Okay, integrating the equation we get the total work. So W is equal to minus integral Vi to Vf P external dV. Also we have to write that W is equal to P external delta V. Okay, so that's about the two equations. W work done on the system. Okay, and this is compression work. What about the expansion work? In the case of expansion work, the external pressure is lower than that of the internal pressure, and the piston moving in the outward direction. The piston moves outward. That is called expansion work. So let's conclude. For expansion work, okay, for expansion work, delta U is equal to Q minus W, because for expansion work W is negative. Okay, for expansion work W is negative. For compression work, expansion work means work done by the system. Work done by the system. You remember that. Expansion work means work done by the system. For compression work, that is work done on the system. W is positive, so delta U is equal to Q plus W. Two equations. For compression work, delta U is equal to Q minus W, or Q minus, one more equation you have to write, delta U is equal to Q minus P delta V. For compression work, delta U is equal to Q plus P delta V. So these equations are very important for doing problems. Okay. As next is a free expansion. The expansion of a gas in vacuum is called a free expansion. What is a free expansion? The expansion of a gas in vacuum is called a free expansion. That means the pressure external is equal to 0. The external pressure is equal to 0. Okay. So no work done or no work is done during the free expansion. Remember that? Free expansion is the expansion of gas in vacuum. No work is done during the free expansion. Why? In the case of ideal gas, there is no work done by the gas at a vacuum. Why? P external is equal to 0. W is equal to minus P external delta V. Okay. So suppose this P external is equal to 0. W is equal to 0. Clear? So the work done is equal to 0 or no work done during the free expansion of an ideal gas, whether the process is reversible or irreversible. Okay, whether the process is reversible or irreversible, the work done is equal to 0. And you remember that as earlier we write the equation W is equal to P external delta V as well as W is equal to minus integral Vi to Vf P external dV. Okay, this is the two equations. This also you know that P external V final minus V initial. All these equations you keep it in your minds. Okay. Then, so that's about the free expansion. Then, according to first law of thermodynamics, we know that delta U is equal to Q plus P external delta V. Okay. First equation you know that. First of all you know that Q plus W, then Q plus P external delta V. Two equations. Okay. And if the work done, expansion work, this is minus. This is for compression work. What about for expansion work? The work done is negative. Suppose the process takes place at a constant volume. Okay. Suppose the process takes place at a constant volume. Delta V is equal to 0. At a constant volume, you remember that delta V is equal to 0. Then what about the work done? Work done, okay, is 0. Because this time becomes 0. So delta U is equal to QV minus P external into 0. Okay. The subscript V denote at a constant volume. The heat absorbed at a constant volume. So delta U is equal to QV. Another equation. At a constant volume, internal energy change is equal to heat absorbed by the system or heat liberated by the system. Okay. So at a constant volume, internal energy change is equal to QV. What the subscript V denotes in QV? It denotes at a constant volume. Okay, a very important equation. If the substance absorb energy or if the system absorb energy, delta U is equal to QV. If the system liberate or evolves heat energy, okay, evolves heat energy or evolves heat, delta U is equal to minus QV. You remember that. The next is isothermal and free expansion. What is isothermal process? What do you mean by isothermal process? The process takes place at a constant temperature is isothermal process. that is delta T is equal to 0. T is constant. Change in temperature is 0, but you remember that T is constant. So isothermal and a free expansion of an ideal gas. So at a constant temperature, the T is constant, that is called isothermal process. So for isothermal process, T is constant. Okay, the expansion of an ideal gas in vacuum W is equal to 0. Okay, the expansion of an ideal gas in vacuum, the work done is equal to 0 since P externally is equal to 0. Also Joule, the scientist Joule determined experimentally Q is equal to 0. So that's why delta U is equal to 0. Okay, isothermal and a free expansion of an ideal gas. Free expansion means expansion vacuum, you remember that. So for isothermal, expansion of an ideal gas in vacuum, W is equal to 0 since P externally is equal to 0. Also, Joule experimentally determined that Q is equal to 0 and therefore delta U is equal to 0. Okay, next is first law of thermodynamics. Delta U is equal to Q plus W for reversible as well as irreversible changes. Delta U is equal to Q plus W can be expressed for isothermal, irreversible and reversible changes as follows. First one, for isothermal irreversible change. Okay, first one for isothermal irreversible change. Reversible change. What is reversible change? We know different process, reversible process, irreversible process, cyclic process, etc. Okay, the process takes place rapidly is called irreversible change. So here, for isothermal process, delta U is equal to 0. So Q is equal to minus W. That is minus P external V final minus V initial. Also we have to write that P external delta V. Okay, so this is the equation for isothermal irreversible change. Next is isothermal reversible change. Okay, for isothermal reversible change, you know an equation W reversible is equal to minus nRT natural logarithm V final divided by V initial. Also we have to write that the natural logarithm is converted into log base 10 minus 2.303 RT log V final divided by V initial. Okay, this is one of the equations you studied that. So minus, so second is for isothermal reversible expansion, reversible change, Q is equal to minus W. So minus of minus plus, so Q is equal to 2.303 RT log Vf divided by V initial. Another equation. Okay, this is the another equation. Also you remember this equation. Minus nRT natural logarithm Vf divided by Vi. Okay, W is equal to minus, sorry, Q is equal to minus W. So minus of minus plus. Minus of minus become plus. So these two equations you remember that. The next is Adiabatic process. Adiabatic process. For adiabatic process, we know that Q is equal to 0. Okay, Q is equal to 0. So for adiabatic process, the third one, adiabatic process, Q is equal to 0. So first law of thermodynamics, delta U is equal to Q plus W. Become, what happens? Delta U is equal to Q is 0, then W. So W adiabatic, another equation. W adiabatic. Okay. Yes, next is significance of delta U. Delta U is equal to Q plus W. For expansion work, delta U is equal to Q minus P external delta V. At a constant volume, delta V is equal to 0, that is delta U is equal to QV. Already we derived this equation, discussed this equation. I want to tell the significance. So this equation represents delta U is the heat change taking place at a constant volume and a constant temperature. What is delta U? What is change in internal energy? It is the heat change taking place at a constant volume and a constant temperature. Okay. Then next we have to discuss about the measurement of delta U. Delta U is measured by a special device called a bomb calorimeter. Okay, bomb calorimeter. Bomb calorimeter. It is devised by Berthelot, the scientist Berthelot. Okay, it is a device used to determine the change in the internal energy. The heat absorbed or liberated at a constant volume, that is delta U. Okay, already we discussed that. And calorimeter is an apparatus which is immersed in one liquid. And by knowing the heat capacity of the calorimeter, we have to measure the internal energy change, that is QV at a constant temperature. So we write QV is equal to delta U. And by using the bomb calorimeter, the heat evolved is equal to minus C delta T into capital M divided by small m. Okay, the equation is very simple. C into delta T into capital M divided by small m. C is the heat capacity of the calorimeter. Heat capacity of the calorimeter. Calorimeter. And delta T is the change in temperature. Okay, change in temperature. Delta T, change in temperature. M is the molar mass of the substance. Capital M is the molar mass of the substance. Small m is the mass of the substance. Okay, you please understand that small m is the mass of the substance taken in the bomb calorimeter, and capital M is the molar mass of the substance. Okay, by supplying the oxygen about a 20 atm pressure, the substance is burned inside the calorimeter. The heat evolved is calculated by this equation, and that is the method to determine the internal energy change. Remember that internal energy change is determined by using bomb calorimeter. Okay, so that's about the first law and internal energy. In the next section, we will discuss some problems based on these concepts and enthalpy. Okay, the new concept enthalpy. Thank you.